Alright, we're back again. Now, this time we are going to solve the inverse Laplace transform of a given function using the rationalization method, or what we call your partial fraction expansion method. Before we proceed with our calculation, we need to discuss first the forms of partial fraction. I will be using my laser pointer here. Now for the distinct linear factor, I will be changing this distinct linear factor. So when we say distinct linear factor, that is the factor of your denominator. Now, I did not write the numerator here. So in your partial fraction expansion, you are actually focusing on the denominator, the factors of your denominator. So in this form, the factors are linear distinct. Okay, s minus a is linear, s minus b is linear. They are distinct. When we say distinct, they are different. So if they are distinct, meaning the expansion should be a all over s minus a plus b all over s minus b. Take note, the degree of the numerator should be less the than the degree of your denominator. For example, if the degree of your denominator is squared, or if the denominator is in second degree, your numerator should be in the first degree or below. Okay. Now, for the repeated factors, take a look at the denominator here. You can see here s minus b quantity squared. This is the repeated linear factor. So I am actually changing this to linear factor, distinct linear factor, and then repeated linear factors. Okay, for the repeated linear factor, this is the expansion. A all over s minus a. Take note, s minus a here is distinct factor. And then I have here b all over s minus b. That is the repeated factor, c all over s minus b quantity squared. So for the repeated factor, first you have to write s minus b with a degree of 1, and then s minus b with a degree of 2. So if that is cube, you can also write here d all over s minus b to the power of 3, or cube. Now for the quadratic factor, just go back to your denominator and analyze if there is a quadratic factor. A quadratic factor is a polynomial having a second degree that is not factorable anymore. Like for example, s squared plus b cannot be factored anymore. So we will leave it as a quadratic factor, and then expanding it will leave you a all over s minus a plus, this is the expansion of your quadratic factor, that is bs plus c all over s squared plus b. That's for quadratic factor. Now for the repeated quadratic factor, you can see here in the denominator you have a quadratic, but it is repeated, so that is the repeated quadratic factor. The same, no, when you expand this one, this is a all over s minus a plus b s plus c all over s squared plus b. Take note, this is the first repeated factor of your quadratic function, and then this one is the next repeated factor. So that will follow, no, from c you have variable ds plus e all over s squared plus b quantity squared. So that's the format. You need to familiarize all the format here so that it is easier for you to solve the problems involving the inverse Laplace transformation of the rational fraction. Okay, now let's have our first example here. Now, in our first example, you have noticed that the denominator is s cubed minus 4s. S cubed minus 4s can be factored out. Now, start your analysis by factoring the denominator completely. So when you say completely, you need to factor this one completely. So what do you think are the factors here? Now take note, s and s here is common. You can take out s. So what will be left? S squared minus 4. S squared minus 4 can also be factored out. What is that? S minus 2 and then s plus 2. So that will give you s squared plus 8 all over s times s minus 2 times s plus 2. These are the factors of your denominator. So we are going to write that. Oh, take note, the factors are distinct. When we say distinct, they are different. Okay. So if that is distinct, then you can expand that using this form. A all over s plus b all over s minus 2 plus c all over s plus 2. Now, in this method, now we are going to solve for b, a, b, and c. Now, the goal here is to solve for a, b, and c. So, a, b, and c can be solved using the COM method. Have you seen COM method? Not yet. So we are going to use the COM method, or what we call the cover up method. So COM method is very simple, compared to the substitution method, the coefficient method. The best way to solve problems using partial fraction is using the COM method. So how does it work? First, now we will rewrite your partial fractions. We will rewrite your fraction, this is your fraction, into its equivalent partial fraction. Now I'm going to change this to a pen. All right. Now to solve for this a, we need to cover s and s here. And what will be left in your fraction here? What will be left? That is 2s plus a all over s squared, s minus 2 all over s plus 2. Now, when you cover s and s here, this is what you will be left. So therefore, you can write that as a is equals to 2s plus 8 all over s minus 2 all over s plus 2, where s equals to a certain value. Where in this case, I use 0. Why 0? Because, take a look at this denominator. What value of s will make this denominator 0? Right? 0. So that is why 0 is the value I use to solve for a. Now, if you are going to substitute 0 to s, that will give you s 8 all over minus 2 plus 2, which is equals to negative 2. Okay, that's the value of your a. Alright. Now, we will proceed to the value of b. Now, to solve for the value of b, we need to cover up s minus 2 and s minus 2. What will be left? Okay, 2s plus 8 all over s plus 2. But in this case, I use s equals to 2. Why s equals to 2? Because to make this denominator 0, the value of s should be 2. Okay? Then, after substituting 2, you have 2 times 2 plus 8 all over 2 times 2 plus 2. Now, simplifying it further, that becomes 3 halves. Alright, now we proceed with C. You cover up S plus 2 and S plus 2, leaving you 2S plus 8 all over S times S minus 2. But I use s equals to negative 2 because if you are going to analyze what is the value of s to make this denominator 0, the value is negative 2. Substitute negative 2 to s and it will give you 1 half. Okay, after substituting all the values, a, b, and c to your expanded version of the fraction, this is the partial fraction, substitute the value and take the individual inverse Laplace transform. So the inverse Laplace of negative 2 all over s is equal to negative 2. The inverse Laplace of 3 halves all over s minus 2 is 3 halves e raised to 2t plus the inverse Laplace of 1 half s plus 2 is 1 half multiplied by e minus 2t. Okay. Okay, take note. Use COM for distinct linear factor. Distinct linear factors only. Okay. All right, I'm back. No, I just charged my laptop we can continue our lecture. Sorry for that. So for our next example, I have here the inverse Laplace transform of 2s minus 1 all over s cubed plus 2s squared plus s. So how are we going to solve this problem? First is to factor out the denominator completely. So how are we going to do that? Okay, first, no, try to assess if there is a common factor. If not, you will be using synthetic division, trial and error to find all the factors. But in this lecture, no, I will make it very simple. So first, factor out s, and what will be left? S squared plus 2s plus 1. And what is s squared plus 2s plus 1? That is a perfect square trinomial which leads to s all over s plus 1 quantity squared. Take note, s plus 1 quantity squared multiplied by s will result to this trinomial. Alright, now after factoring the denominator completely, take note, no? After factoring the denominator completely, take a look at the denominator and see the form. In this case, no, it has a repeated factor, okay, as indicated by quantity squared here. So what you are going to do is to go back to the forms of uh, the partial fraction and then rewrite that into its expanded form. In this case, this is a all over s, that is the factor s, b all over s plus 1 for the first repeated factor, c all over s plus 1 quantity squared for the second repeated factor. Right. Now, we can only use COM method to solve for a and c. Take note. No? To solve for A and C, no, we can use COM method. Why COM method is only for A and C? Why not B? Because B is not found in your denominator. Okay, I will erase this part first. Okay, erase all ink. Okay, okay, I erase all ink. Now, S here now is found on A. Okay, S plus 1 quantity squared here is found on C. That is why only A and C can be solved using the cover up method. Let's try to solve A first. But before that, we need to rewrite, no, the fraction in its expanded form. Okay, this is the fraction and this is the expanded form. Fraction, expanded form. Now, to solve for we cover S and S. Never mind this term. Now, we are only dealing with A here. So, you just cover S and S. What will be left for your A? What will be left for your A? This will be left for A. 2s minus 1 all over s plus 1 quantity squared and set s equals to 0. Why 0? Because to make this denominator become 0, the value of s should be 0. That is why 0 is the value of s here. So substitute 0, you will have negative 1 over 1 minus 1. That's the value of A. How about the value of C? How are we going to do that? Because this is a repeated factor. If you will notice, that is in squared. We can do that by taking its derivative. Okay, now, this time, now to solve for C, we cover up s plus 1 quantity squared. And what's next? What will be left? Okay, this term will be left 2s minus 1 all over s. But take note, we will use derivative here. So in your calculator, try to plug in this expression, the derivative. In your calculator, you use x, of course. The derivative of 2x minus 1 all over x, that is in your calculator, and set the value of x equals to 1 in your calculator. Then press enter. What will be the result? Right. the result would be positive 1. So try to do that in your calculator. In your calculator, you have your derivative function. Okay. Now, we have the values of A and C. Now, our next step is to solve for B using the coefficient method. To solve B using the coefficient method, this is your step on how to do that. First, no, you are going to rewrite the fraction. This is your fraction. And we will multiply the fraction. Take note, this is your fraction and this is your partial fraction. We are going to multiply the whole of this equation by its LCD. Do you know what is LCD? LCD is the least common denominator. Now, LCD is actually your denominator here. That's the LCD. So you have to multiply the whole of this equation by its LCD. Okay, now multiply this to that value. What will be left? Right, 2s minus 1 will be left. Multiply this LCD to A. What will be left? A times s plus 1 quantity squared. Correct. Multiply this to that term. What will be left? S plus 1 will cancel out. S plus 1 will remain since the power here is 2. So B times S plus 1. Multiply that to C. That will be C times S. And that will be the result of your multiplication of the LCD in your equation. So here we have 2s minus 1. We have A times S plus 1 quantity squared. For the next term, we have bs times s plus 1, and then for the last term, we have cs. Take note, we already have the value of A and the value of C. Then substitute that value. A is negative 1. We have solved that a while ago. And C is equal to 1. All right. Then what are we going to do next? We need to use the coefficient method. But before that, we need to expand this binomial. Okay, that is s plus 1 quantity squared. Do you know how to expand that? Okay, square the first term, that is x squared. Multiply the first term, s. The second term, 1. Multiplied by the exponent 2, that will become 2s. Square the last term, that's 1. So that will be s squared minus 2s plus 1. So quantity squared should not be here. So I'm sorry, no? You erase that one. We will erase the quantity squared there. All right, then we are going now to solve for b. Take note, if we will multiply, we will distribute b here, this will become b squared, right? And the coefficient of s squared here is negative 1, right? Now, if we are going to solve for the coefficient of s on this left side of the equation, we don't have s squared here. So we put 0. So copy the equal sign. In the right side of the equation, we have negative 1 as the coefficient of your s squared, negative 1. And b here is the coefficient of s squared. Therefore, if we are going to transpose negative 1 to the other side of the equation, you will have b equals to 1. Now we completed the values of a, b, and c. In our next slide, we are going to substitute the values to your partial fraction. A equals 1, A equals negative 1, B equals 1, C equals 1. So that will be the value. Then take the inverse Laplace transform of each term. How are you going to do that? Oh, take the inverse Laplace transform negative 1 over s. That's negative 1. Take the inverse Laplace transform of 1 over s plus 1. That is e raised to minus t. What about this? What is the inverse Laplace transform of this? We have discussed that a while ago. So now if taking the inverse Laplace transform of each term, now this will be left. Take note, in the third term, you have your shifted S value. If we are going to take out 1, that will result to e raised to minus t, leaving you s squared. And we know what is the inverse Laplace transform of 1 over s squared. So take the Laplace transform of this. Okay, I'm sorry, this should be positive because negative 1 was transferred to uh, before your inverse Laplace transform sign. So the final answer would be negative 1 plus e raised to minus t plus e raised to minus t times t. So the Laplace transform of this is equivalent to t. Alright, that's it for the repeated quadratic factors. I know that this topic is very complicated, especially if the fractions are really hard. Okay, let's try this one. Okay, I don't want you to get confused no, on the third example. Okay, this will be the last example. Okay. Quadratic. Now this involves quadratic factors. So I have here 3s plus 5 all over s cubed plus s squared plus s. Take note, we need to factor out the denominator completely. So factoring out the denominator will lead you to a quadratic equation. A quadratic factor, I mean. Take a look at this one. This is your quadratic factor. This is your quadratic factor. So this example is actually a complicated one. This is a really hard example because of the presence of s. If s is not here, now this will become a simple one. Now let's try to solve this. No, let's try to solve a complicated example because in your assignment, now most of your assignments are complicated. Okay, let's start. We will transform this fraction into its equivalent partial fraction expansion. Okay. After that, we are going to solve for the values of a, b, and c. But we can easily solve a since a has a linear factor, okay, s. So for a, in the case of a, we can use the com method to solve for A only. Why A only? Because A have a linear factor in the denominator. Okay, to solve for A, use com method. So before using com method, we need to equate the original fraction to its expanded or partial fraction. Okay, now to solve for A, we need to cover S and S. Take note of that. We can only use the com method for linear factor. Now, what will be left? A is equals to 3s plus 5 all over s squared plus s plus 1. Now, we will set s equals to 0 because to make this denominator 0, the value should be of s should be 0. Substituting 0 will leave you to the answer equals to 5. Okay. Now we go to the values of b and c. The values of b and c can be solved using the coefficient method. So for the coefficient method, we need to copy again the original fraction, equate that to its partial fraction, and then multiply this equation by its LCD. Just like what we did on our previous example. We multiply the whole equation by its LCD, and LCD can be found here. So this is your LCD. So distribute this one to that term. No, that will give you 3s plus 5. Distribute this LCD to this term, that will give you a, s and s will cancel out, that will be a multiplied by s squared plus s plus 1. Distribute this to this term, what will be left? S. So s times s, that will become bs squared, s times c, that will become cs, that will give you 3 plus 5 equals to a times s squared plus s plus 1 plus b s squared plus cs. Okay, since we have the value of a, we can substitute that no, before we use the coefficient method. Substitute a to 5, and then use the coefficient method. We will start with the coefficient of s squared. We don't have the coefficient of s squared here, so we put 0, which is equals to, here, the coefficient of s squared is equals to 5, so we write 5, and the coefficient of b of s squared here is b, so we write b. Now, if we are going to transpose 5 to the other side of the equation, that becomes negative 5. That's the value of b. Now, let's try to solve the coefficient of s. So in this side, the coefficient of s is 3. So we write 3 equal to, in this side, the coefficient of s here is equals to 5 when you distribute 5. No? So the coefficient of s here is actually 5. And the coefficient of s here is c. So if we transpose 5 to the other side of the equation, that will give you negative 2. Okay, is that clear? Now we have the values of a, b, and c. Now we are going to substitute the values to your partial fraction. Okay, this is the hardest part because of the value of s here. Okay, it becomes harder because of the value, because of s. Okay, if s is not there, that is a very simple problem. But let's try. Let's try to solve this problem using the method that we've learned, no? The 4B method, the buka-buka, bika-bika method, the divide and conquer method. Okay, for this term only. So the first thing that you should do is to factor out 5, negative 5. No? We will factor out negative 5. So that will become negative 5 times the inverse Laplace transform. Take note, 5 was factored out here. That will left you s. And the 2, no? When 5 is taken out, that will give you 2 over 5. Now take note, review your factoring. Now you can check that by multiplying negative 5 to the terms. Okay. Now, just like in our previous example, we need to make this a perfect square trinomial. What is that number? What number should be added to s squared plus s to make it a perfect square trinomial? Think. Okay. Okay, let's do what we have discussed before. Take the square root of that s, multiply that by 2, 2s, right? So this term s will be divided by 2s. What's the result? 1/2. Good. 1/2. What is 1/2 squared? 1/4. Right, 1/4. Now you are going to add 1/4 to s squared plus s, so to make that perfect square trinomial. So meaning 1/4 can be found here. You can split 1 to 1/4 and 3/4, just like what we did now in our previous example. So we split 1/4, 1 by 1/4 and 3/4, so that we can group this term and factor that out later on. All right. Now this is the copy of the previous slide. Next thing to do is to group this s squared plus s plus 1/4, and then later on you factor that out. Why do we need to factor that out? Because we want to factor that out so that we will know what is the amount of shift in your s domain. So in this case, the amount of shift is 1/2. Take note, s squared plus s plus minus 4 plus 1/4 is the same as s plus 1/2 quantity squared. So here, 1/2 is the amount of shift. That is why in your numerator, I put 1/2 minus 1/2. 1/2 minus 1/2. So that now when we when we split the two fractions, no, it will give you the same shift on your first fraction. So what are we going to do next is to simplify this one because they will be splitted later on. So you need to simplify it now. So what is the simplified form? That's negative 9 over 10. All right. Now, after simplifying, we are now ready to split the fraction. In your next slide, the fraction is splitted into two. This would be the inverse Laplace of that and the inverse Laplace of that term. Okay, take note, I take out 9 over 10. Okay, here, going back here, what is missing in your numerator? What is missing here? Correct, square root of 3/4. So square root of 3/4 is missing here because this is your b, this is your b squared. So square root of 3/4 is missing. So if I'm going to multiply, by the way, if I'm going to multiply square root to the numerator, okay, this is square root to the numerator. Okay, I will be using my uh, laser pointer. Okay, where's my laser pointer? That's it. Okay, multiplying the numerator by square root of 3/4 and then dividing that outside the inverse Laplace transform sign by by square root of 3/4. Take note, we need to simplify this constant term. And also, we need to simplify this to make our Laplace transform easier. And plus some to the i's, of course. Okay. Now, in the simplified form, we take out the amount of shift, which is 1/2. So taking out negative 1/2 as the amount of shift will give you e raised to minus 1/2 t. This will also give you e raised to minus 1/2 t. And 1.04 is actually the simplified form of 9 over 10 over square root of 3/4. Okay, that will give you 1.04. And square root of 3/4 will give you 0.87. Alright, now it is easier for us to take the inverse Laplace transform. Okay, let's try. In your next slide, no, I have rewritten the equations, the previous equation. Okay, now our goal is to take the inverse Laplace transform of this. This is in the form of cosine. This is s all over s squared plus b squared. But in this case, your b squared is equals to 3 over 4. So what is the inverse Laplace transform of that? Okay, think. This is s squared plus 3/4. Take note, square root of 3/4 is 0.87, as I have mentioned a while ago. Now, if you are going to take the inverse Laplace transform this is just the same as cosine of 0.87. The square root of 3/4 is 0.87t minus 1.04 e raised to minus 1/2 t multiplied by sine 0.87t. Take note, this is the square root of 3/4. That's 0.87. Any question? Mm-hmm. None so far. Oh yes. Though the next thing that you should do is to distribute this 5 to each of the terms. So distribute 5 and you will have your final answer. This will be your final answer. Alright, no? This is the end of our lecture video for the inverse Laplace transform. My next lecture video will focus on the applications of Laplace transformation. So if you have any questions, no, feel free to comment on my video in YouTube. And also don't forget not to message me if for some clarification. Now, I want you to video blog for this day about what you have learned in your lecture video and what part of the lecture video is the most challenging part. No. Okay. See you next meeting. Stop recording.